Final thing I will comment on here is something that you should know about, but doesn't affect you all that much in what you're doing because I've given you the skeleton for doing this. So when we produce the global matrix is a matrix which is number of degrees of freedom by number of degrees of freedom, which is big. Nonlinear functions do that to you, right? It's got number of degrees of freedom squared entries. And if you had, say, a 64 by 64 unit square, which is not that big a mesh, and you did degree 4 Lagrange finite elements, which is not that high order, you suddenly discover that that matrix would have 4 billion entries and would take 35 gigabytes of memory to store, which is probably several times what's on your laptop. It's probably what's more than what's on these desktops as well. Also, almost all of those entries are 0, because you only get non-zero entries in the matrix in the overlap between two basis functions, and two basis functions only overlap if they are topologically near each other in the mesh. And so as you make the mesh bigger and bigger and bigger, what you're doing is adding more and more elements which are topologically far away. And so the number of non-zeros on a mesh is approximately, on each row of a mesh, is approximately constant regardless of the size of the mesh. So this is horrifically wasteful. Also, even if you manage to assemble this guy, what's the next thing you're going to do? The next thing you're going to do is call a linear solver on this, and the linear solver is going to spend, to a very good approximation, all of its time multiplying by 0, which is horrifically bad. So we don't do that because it's dumb. What you do instead is you realize that a matrix isn't actually the same thing as an array. So an array is a set of values in memory. A matrix is a mathematical object. And a matrix as a mathematical object is perfectly good if it's got the mathematical operations that a matrix ought to have. So in particular for solvers, if it's a iterative solver, you need to be able to multiply by a vector. If it's a direct solver, you need to be able to look up the values in the matrix. So you didn't need to store that necessarily as a list of values in memory. That's just one way of doing it. In fact, a very, very common way of doing it that works really well for iterative solvers, so it's very widely used for PDEs, is something called compressed sparse row format. So what we do is on each row, we store a vector of non-zero values and a vector of the columns that they belong to. So now you can find where in the matrix all the non-zeros are. And it turns out that that's very efficient for doing a matrix vector multiply, because what you do is you look up the columns in the vector and dot product what you got back, and that gives you an entry in the output vector. And that only stores twice number of non-zero values. So that's very, very cheap. There is also coordinate format, where we literally just store a list of coordinates and non-zero values. If you know in advance where the non-zero off-diagonals are, and that is true if you have a very structured mesh, then you can also store something like CSR, except you don't bother to even store what the columns are because you know in advance what they are. And so, but all of those are sparse matrix formats that store for a length n problem, they store order n values instead of order n squared. So the reason you care about this is scipy.sparse provides sparse matrices, and in the skeleton code, I give you a couple of those. If you are feeling curious, you can switch which sparse matrix format is in there. I very, very, very strongly recommend that you do not switch it to a dense format, because what you will do is enjoy watching your computer freeze and eventually run out of memory. And if that's your idea of a good time, you can do that, but on the whole, probably not.